Correct, yeah. So thank you for the invitation. So this is joint work with my PhD student, who is Jake Sudbery, and many helpful discussions with Ronnie Pavlov. Okay, so I'm going to define the Ellis semigroup, and then we're not really going to talk about it. So we are going to talk about it, but I'm never really going to do any ugly stuff, so don't worry. So if I have a dynamical system, a topological dynamical system, not necessarily invertible, in fact, it will not be a dynamical system. And in today's talk, X is a Cantor space, and sigma is the shift, okay? So the Ellis semigroup is just the compactification of the action with the topology of pointwise convergence, all right? So it's a set of all f from x to x, where f is some limit, according to some net, of powers of, in this case, the shift or elements of the action, okay? And this is in the topology of pointwise convergence. So what this means is this has to be true pointwise. If I put an x here and I put an x here, this is true. Okay? So generally, this thing is very ugly. It's very difficult to compute. Okay? So, and that's why we're not really going to talk about it. Okay? So generally very difficult. But there's a result from 1995 by Angela Köhler, which is the following, okay? She says either the Ellis semigroup has cardinality less than or equal to cardinality of the continuum, or the Ellis semigroup has cardinality 2 to the continuum. Okay, so this is the dichotomy. Okay, so this is huge, and generally speaking, if you're in this camp, then it's very difficult to say anything about the Ellis semigroup. Okay. In this camp, it's almost tractable. Right? So, so a question is, what Ellis semigroups are actually tractable? So these are called tame dynamical systems. And otherwise they're called non-tame. Okay, so that's the dichotomy. Okay, so so once Köhler's result came out, there was a theorem in 2006 by Huang. Which said the following. It said that if X is tame, then X is almost automorphic. I'm going to tell you in a minute. So actually, we are looking only at minimal dynamical systems. So there's one point. So let me explain what almost automorphic is. It means that, i.e., if I consider the maximal equicontinuous factor map, so I'm just going to write MEF for the maximal equicontinuous factor. So this is like the largest group rotation that appears as a factor topologically. Okay. Then for minimal systems, the cardinality of all X such that pi inverse of pi of X equals X is greater than 1. Is at least 1. In fact, that's all. Okay, so somewhere you're injective. Okay, so So this is a necessary but not a sufficient condition, okay? So let's look at an example. So example is if X is the Fibonacci shift. Okay, so I'm not going to define it, even though most of you know it, but let me try and tell you why, because I'm going to define the Tribonacci shift in a minute, okay? So let me just try and tell you why. So the reason, intuitively, is if you look at the set of all x such that pi inverse, okay, so the Tribonacci shift is almost automorphic. The maximum IQ continuous factor is a circle. It's just a circle rotation, right? And I think many of you know this better than me. The set of x such that they live in a singular fiber, okay, is basically up to an orbit exactly one element, okay? So this is countable. Okay, so that is the reason why X, the Fibonacci shift, is tame, okay? So is tame, I should have written that. Okay, i.e. its Ellis semigroup is not large, okay? Okay, so example 2, what about X, and I know I'm going to write X theta is the Tribonacci shift. Okay, so my question is it tame? Okay. And there was an answer to this question in a paper by Glasner and Megrelishvili. So I've sort of been aware of it for a little while, but I know it appeared in a transactions paper in 2022, and they said that the Tribonacci shift is tame. Okay. So I was interested to see why is this true, and let me tell you what they said. Okay. So this result by Huang, which is that if it's tame, then it's almost automorphic. So they based this on two observations. And the first was they made a finer statement here by Huang. So yet another definition is going to come up, is that if pi from x theta into its maximal equicontinuous factor, which is some torus here, is, so maybe this is just a general fact, is strongly, I put a line because I haven't defined this, strongly almost automorphic. Then X is tame. And then they combined this with a result that they quoted Timo Jolivet, who wrote that Tribonacci, in fact, they also said it for the Brun algorithm and substitution. Tribonacci is semi-conjugate to a rotation. Okay? So with these two, so they said, so you need to know what these definitions are. So what does strongly almost automorphic mean? It means that this is true. The set of discontinuities in your maximal equicontinuous factor map is countable. Okay? So that's what this means. And according to them, Jolivet had shown that Tribonacci shift is semi-conjugate to a rotation, and their definition of semi-conjugate was that it had that this was countable. Okay, which is not true. So there was some confusion. So this was not convincing for me. Yeah. Mm-hmm. Mm-hmm. No. No. And this is a measurable thing. Tribonacci is not topologically conjugate to a rotation. Yeah, no, I know. Yeah. So if it's topologically conjugate to the Fibonacci tiling system, then yes, I think it is tame. But this is not. Tribonacci is not. Yeah, the point of Tribonacci is that the set is not countable. In fact, Pierre talked about the Rossi fractal, and the set of points where this map is not countable is the border of the fractal, the boundary of the fractal, which is not countable. Okay? So I remember a paper by Bernard Ost, who wrote in French that Bloch claimed that something is recognizable, but their proof is not convincing. So I don't think this proof is convincing. So what do you think? Do you think Tribonacci is tame or not? Okay. Okay, so I'm going to talk a little bit about word combinatorics. I'm going to talk a little bit about randomness. So this is sort of related to uniform substitutions, and I have 15 minutes. Okay. So the first thing I'd like to do is actually define the Tribonacci shift. Okay. So theta is a transformation. A goes to AB, B goes to AC, and C goes to A. And I'm going to work with the one-sided Tribonacci shift. Okay, so there is a unique. So if you can show things for the one-sided Tribonacci shift, then it will also be likely true for the two-sided Tribonacci shift. So I take the infinite word, which is the fixed point, starting with A. Okay, and so x theta is defined to be the shift orbit closure of U, and here U is n is non-negative. Okay, so that's the shift. And for later purposes, I'm going to take the projection, and I'm going to call it A goes to 0, and B and C go to 1. Okay? Of U, I'm going to define that to be V. So I just collapse all B's and C's into that. So there's another way to look at this. This really is a topological conjugacy. Okay? So I'm going to define XB to be the set of all infinite sequences of zeros and ones, where I do not see 3 consecutive ones. Okay? So a set of all sequences where I don't see 3 consecutive ones. And I'm going to define a map as a successor map. Okay? So phi of x is equal to, and it will become clearer what I mean by this in a minute. Okay, so I map x to its successor. Okay, and if x is a maximal path, and there are 3 maximal paths here, I map them all to the minimal path. Okay, so I'll give you an example. So M, which is all zeros, is minimal, and M, there are 3 of them, so I'll draw one of them. It could be 1, 1, 0, 1, 1, 0, 1, 1, 0. Okay, there's a special kind of addition because I'm doing, I have to stay in my space. Okay. Those of you who know Bradley-Virchow systems, this is basically a one-sided Bradley-Virchow system. Okay. And it is not too hard to show that as topological dynamical systems, so this is a topological conjugacy. That's true. And there's a map here, which is going to be pi. And what did I call it to? I called it the first level map. Okay, so pi goes from x into 0, 1 to the n. Okay. So what is this? This is defined as follows. Pi, so I'll just call it first level map here. Pi of such a sequence is I take e to the, let's call this x. Yeah, I mean xb. I was debating whether to include the b. Yeah, so b is b for badly, but if you want to put it, yeah, so here too, thank you. Okay. So this, basically, I take an infinite sequence x, I look at its image under the +1 map, and I project down to the first level. Okay? And in fact, this projection is not so different to this projection. Okay? So basically, what I can say is if x is in x theta, then what do I want to say here? I want to say that the projection onto, what did I call it? A goes to 0, and B and C go to 1 of x at level n is equal to, in fact, this is just equal to, of f of x, where this is by in the map f. Okay, so this is just a long way to tell you that, in fact, this system tracks this system very, very well. Okay, so we can leave this for the time being. Now I'd like to talk a little bit about numeration, and then some word combinatorics, and then some randomness, and then I'm done. Okay, so the first thing I want to say is I know that you all know this Tribonacci numeration system. Okay, so numeration. So I define t minus 1 to be equal to 1, t minus 2 to be equal to 0, t0 to be equal to 1, and then tn to be tn minus 1 plus tn minus 2 plus tn minus 3, right? So the sequence looks like this, and exceptionally, I'm going to move it to the right. Even though this is a private joke between Olivier and myself, we can never decide which way to make things go. Okay? And so on. This is T0, this is T1, T2, T3. Okay? So you know that every natural number has a unique expansion. Let's call it n base t, right? And this n base t is in that space xb, right? So it's eventually 0. There are no 3 consecutive ones, right? So that's, and conversely, I can say, conversely, if you give me any word on any digit set, I can define is a number, right? So this is a finite word. Okay? I can expand it using the Tribonacci expansion. Are there any questions? Okay, T is the Tribonacci numeration. So maybe I write T is equal to this numeration system. Okay? Okay. Okay. So now this is where Ronnie came in. He knew about a paper by, so this is a paper by Kamai and Zamboni from 2002. So this is the word combinatorics part, right? So somebody mentioned complexity earlier, so they defined something called maximum pattern complexity. So given a sequence, right, the maximal pattern complexity function is the supremum. Okay, so you basically take all possible index sets, right? So 0 is equal to tau naught is equal to tau 1. Sorry, it's strictly less than tau 1. Strictly less than tau k minus 1. And now what am I going to do? I'm going to take the cardinality of all words that I see, n plus tau 0, x n plus tau 1, x n plus tau k minus 1 as n varies. Okay? So the standard complexity function, you've got a sequence, this is my sequence x, and you look at all words of length k, which are indexed by a contiguous interval, right? So these guys were interested in the number of words that you could see where you were allowed, so this would be x tau 0, x tau 1, x tau 2, x tau 3, and so on, right? You don't have to be contiguous, okay? And what they showed, so this is these guys, what they showed is if you take this sequence, which is the fixed point of the Tribonacci sequence, and you project it to 0 and 1, so V is the projection, so A goes to 0, and B and C goes to 1, then this is what they call the maximum pattern complexity. Okay, complexity function. They show that this thing, there's a U here, where U is the fixed point, okay? For this one, the maximum pattern complexity is 2 to the k. Okay? So that's quite large, right? It basically means that there is some pattern, and they even explicitly found it, such that if you look along those indices, you will see all words of length k. Okay? And in fact, their proof is explicit. So their proof is quite nice. Okay? Yeah. That's right. It is not null. Correct. Yeah. Okay. So how did they do this? So they actually explicitly defined this. So they defined tau I, and it's related to this numeration system, is equal to tau 4. This is just a computational, like it's just a calculational thing, which I'm going to put in anyways, plus tau, what was it? I'm going to screw this up. 6i plus 4. Okay? For I from 0 to k minus 1. Okay? So it's a Tribonacci number. Sorry, this is, yeah, that's right. This is going to be, whoops, T4, and this is going to be T6i plus 4. Okay, so they actually computed it, and then what they show, this is a very nice thing. This one here? No, that's a tau. That's going to be the window that I look at. So the window is separated exponentially as these things grow, right? I mean, this is zero entropy sequences, so yeah, you would expect the... Okay, I'm not going to tell you what I was going to say because that will give you the answer. But anyways, so what did they show they showed that if you give me a word of length k minus 1, okay, and if you consider the following n, okay, so this depends on omega, the word w or omega, okay, so it's going to be the number whose Tribonacci expansion is the following: 1, 0, 0, 1, w naught 0, 1, 0, 0, 1, w 1, 0, 1, 0, 0, 1, wk minus 1, 0. So if you take the number which has this as an expansion, I will continue on the next line. Then, and this I have to Vn, so this n depends on the omega, right? Or the w, whichever, okay? Vn omega minus, so like I said, this is a stupid computational mistake, sort of necessity, plus tau of I is wi. Okay, so that's quite nice. Okay, and another way to say this is if x is equal to phi to the n. So phi here is this map, the successor map here, phi to the n of all zeros. Okay, then I would say pi level 1 of x. This is just a fancy way that will help me in a minute. I know I have 3 minutes left, right? Tau I minus T4 is Wi. Okay, so what's interesting here is that the sequence is nested. Okay, so I can say definition. I'm going to define an infinite sequence, okay? So I'm going to say tau I is defined to be T4 plus what? Plus T, well, I wrote it over there, 6I plus 4, where I is greater than or equal to 0, okay? So that's where the word combinatorics came from. There's a result where the randomness comes in. So this is a result also due to Köhler, but was in 95, but was, I guess, brought into the Ellis semigroup by Karen Lee in 2007 or 6, okay, which is that X is non-tame if and only if X has an independent sequence. I'll give you the definition in a sec. So what is an independent sequence? So definition, so I'm just going to define it for like n actions or z actions. So I say a sequence of indices is an independent sequence if for any word that you give me, and now my w or omega is going to be in 0, 1 to the n. Okay, so any choice function that you give me, there exists a point in my space, okay? It's an independent sequence for a dynamical system x sigma, say. Okay, I can find the point, and this is, I'm just going to state it for shifts now. There exist two cylinder sets. Okay. There exists an x and x such that x n k is equal to wk. Okay, so what this means is that there is a sequence of indices, n1, n2, potentially exponentially increasing in distance, the distance between them, such that if you give me any sequence of zeros and ones, okay, so maybe this should be in CWK, sorry, in CWK, then, so if it's just cylinder set zeros and ones, I find W0 here, W1 here, W3 here, and so on. That's an independent sequence. So basically, there's a sequence of indices along which you see the full shift. Yeah, the WK is just indexing which one you see. That's all. Okay, so I'm going to stop now because this is an independent sequence. Okay? And therefore, it ain't tame. Okay? So, corollary is the Tribonacci shift is not tame. Okay? So I think I'm going to stop now. Thank you.